So if I go to the, so I'm going to do hybrid MPI and OpenMP, and then for this morning. So what I'm going to do is I'm going to do an introduction, then you're going to familiarize yourself with the exercise, and then I will so I'll talk about the issues and the concepts in the first half of the lecture, and afterwards we'll talk about the actual implementation. But I thought I would very briefly outline what the exercise is going to be, just so you had a mental model of what we're going to be doing. So I'm just going to grab the code. So the code is here for the exercise. I'm going to be using the traffic model. So this is an exercise sheet, but I wanted to basically show you how this works very briefly. So what I'm going to do is I will now share my login window. Okay, so what I'll do is I'll get that software. You could okay, you can get it in various ways, and I'll unpack it. And you'll see there's lots and lots. I've given you a whole bunch of stuff here. There's more than you need, but I have implementations of this traffic model in C and Fortran, in MPI, OpenMP, and Serial, and also there's even Python here, and some reefs. There's some stuff here, and there's other stuff here. But I think I'll show you. I'll take you through the code just so we can get up to speed. So if you're not familiar, I cover this model in my introductory course, but just in case you're not familiar, I will basically very briefly go through it. I'll just show you one slide here to show you how it works. Okay, sorry, I shared the wrong screen. So it's a very, very simple cellular automaton model. And so the idea is you have a road divided into cells, and each cell is either occupied or unoccupied. And these turn out in the code to be ones and zeros. Okay, so we have a 1 for a road, a cell which is occupied, and a 0 for one which isn't. And the only rule is that a car moves forward if it can and not if it can't. So we go through a series of time steps. Some of you may be familiar with cellular automaton models like the Game of Life, which is a 2D one. This is a very, very simple one. So what you say, you don't move a car. You don't say, well, that car moves, then this one. What you say is that car can move, that one can't, and that one can, and then you move them. So and now you say that car can move, and that one can't, and so you move them again. And actually, we'll see now that when we're in this situation, they can move whenever they like. And that's basically it, okay? That's basically the model. And what you'll see is that the important point is the state of a cell depends on the state of its nearest neighbors. To update the cell, you need to know what's happening here and here. And that means in the parallel code, in the message passing code at least, we need to do halo swapping. We need to do boundary exchange at the edges. So that's really all there is to the model. But it's a useful prototype for message passing for very simple situations. So what I will do is now show you the code. So let's go into the C serial code, for example. Okay. You'll see there's a bunch of stuff here. Sorry. There's the traffic. So I'll look at the. So I'm doing a very big road. Number of cells is 32 million, I think. I allocate the road, and you'll see that it's too bigger than you'd expect, and that's because and we have an old road and a new road. And each iteration we set the new road based on the old road. The road is slightly bigger than you think because we have periodic boundaries. These turn out to be the halos in the parallel code. In the serial code, they're just there to implement the periodic boundary conditions. And we initialize the road. We have a target density. So the road starts off as slightly more than half full. I initialize the road randomly. Okay. It's called init road. but they're not that important. It just uses the random number generator to initialize them, roughly 50-50. And then I basically loop over a bunch of iterations. I update the boundary conditions. That's just a copy in the serial code, and the parallel code that, of course, will imply message passing. I have a function nMove. I work out how many cars move, and it's called update road. The new road is updated based on the old road, and it's n cell long, and then I copy back for the next iteration. So that's really very simple. So all you're really interested in is the update. Okay, this is the initialization routine, which just uses a random number generator. It's not that interesting, but the update road is the interesting thing, and you'll see that it just basically, I'll need to make it a bit bigger. There we go. It loops over the road, and it says if the old road is full, if the cell up the way is full, then it doesn't move, else it does move and it becomes empty, and I increment the number of moves. Else, if the current, if we're empty, if the road down the way, old road of I-1 is 1, then we become occupied, else we stay unoccupied. That's basically it. It's very, very simple. So I can make that, hopefully that makefile is correct, and I can just run it in serial, and you'll see that it basically computes the average velocity is the number of cars divided by the number of cars that move divided by the total number of cars. And so, and this figure here, 408 megacops, is mega car operations per second. The update rate was I updated 408 million cars per second, or cells per second. So I mean it runs, but we're going to parallelize it. So let's look at the MPI. It's very, very similar. We start off with n cell, old road and new road, but what we do is we have an n local. So basically, you know, we have n cell is 32 million, but if we're on size processes, say 10, then each process will only have 3.2 million. So we only allocate the local road, and we basically we initialize. There's a bit of setup. We have to initialize on the root processor and scatter the result. But that's just setup. Okay, so I do the initialization on a single process to make sure that I get the same answer in parallel as in serial. But that's not really very interesting. I compute my neighbors, and this is just a trick that this is periodic boundary conditions. So the up neighbor of rank size -1 is 0. The down neighbor of rank 0 is size -1. And all I do is we do a halo swap. So I've done it with send receive here, which is not particularly efficient, but I just do it for simplicity. I have the same, but the important point is, having done the halo swapping, this n move local is update road is exactly the same function. And then I get the total number of moves with an all reduce. And that basically is all there is to it. And so let's see if we can compile that. Now I'll have to have a script here, and I want to do the reservation. And today the reservation is called, what's it called today? Give me a second. I've got it on the website. It is thanks. I think I have it cut and paste here. There we are. So we have a different reservation today, Werner. So today it's a different one. Oh no, actually you're right. Apologies. I've done something stupid. You're absolutely right. Apologies. That's yesterday's one, isn't it? Thank you. It must be a 818. Okay. So I should be able to. So let's run on. Let's just check that on one node. Well, let's do 2 nodes and tasks per node is 128. So running on 256 processes. See how we're going. It's running. And we have an output here. So, okay, I print the running pressure passenger traffic on serial, which is stupid. I get 256 of them. But there we can see that, let's just check with, actually, so what we want to check is here, the iteration on, the average velocity iteration 100 is 0.898955. We should get the same answer in parallel, and we do, but it ran at 26543 megacops, which is, how many times faster is that? That's about 60 times faster. Now, there's reasons why it doesn't scale perfectly, but it goes a lot faster and we get the same answer. But what we're interested today in is also looking at OpenMP. And OpenMP is a model which allows you to spawn threads. It's based on threads. So but the important point about OpenMP is limited to a single computer, a single operating system, or in high performance computing techniques, a single node. So OpenMP is very useful for parallelizing on your laptop or on a workstation. But if we were to use OpenMP on ARCHER2, purely OpenMP, we couldn't run on more than 128 processes. In fact, what I will do is I will run the traffic model on, we're going to compare the performance of pure OpenMP and pure MPI. So I'll just run on one node, 128 tasks, and let's let that run while I go back and show you the traffic model. So the traffic model in OpenMP is very different. It looks like a serial code. This is identical. In fact, it's almost identical to the serial code. All we have to do is we use directives. So OpenMP works with compiler directives. Hash pragma OMP parallel spawns a parallel region, creates a lot of threads. In this case, we're going to do 128. And then that's just, and we're going to print here. So it's a very different model from, if you're familiar, a very different model from MPI. OpenMP is based on threads. You run a single program, it spawns lots of threads. This code is all exactly the same. Now, I parallelize the update road, but I also have to parallelize the copy back, and that's very simple. I just say do this in parallel. Hash pragma OMP parallel says do this in parallel on lots of threads, and I say that these arrays are shared between all the threads, and I do the copy back. But the interesting thing is, of course, the traffic lib, and so that's exactly the same. But the update road, you'll see, all I have to do is to parallelize it. Is I just say hash pragma OMP parallel 4, and the old and new road are shared arrays between all the threads, and this nmove is a reduction variable, just like you specify in equivalent to you do in MPI, and you have to tell OpenMP that to allow it to accumulate the value across different threads. And in fact, if you look, it's an incredibly simple. If I diff this with the serial code, you'll see that the differences are literally. I've got a typo here, must be spaces, but literally, other than a few print statements, there's a couple of parallel regions, and include the OpenMP. I don't know why that's different. There must be a space issue there, or the traffic lib.c. Let's do that again. I just use a different timing routine, but literally for the update, that's the only difference. Is just you tell it to do it in parallel. So let's make, and the important point is that because the compilation is because the parallelization is done by the compiler, you need to turn OpenMP on in the compiler, and that's -f OpenMP. And you need to do a different back script. Where it's important that you're running only one task. With OpenMP, you run one program, so it's not like MPI where you run 128 programs. You run a single program, a serial program, but at runtime, it spawns these threads. And the way you tell it to do 128 threads is you say OMP num threads equals 128. And this is just a hint to the runtime system. So let's submit that. And it's running. It's finished. So let's look at that. So we'll look at the MPI first. No, what was it called? Traffic dash dot out. Did it run correctly? It did. Okay. And it will look at also the one I just ran for C, just to check we compare the performance, and that'll be the last one, which is 197355 dot out, I guess. So hopefully you can see that. So I have to scroll past all this stuff which I stupidly put in the MPI. There we go. So you'll see that. So this is running on 108 threads. This is running on 108 processes. Okay, but hopefully the answer is the same. So actually the so 5 which is faster, is that okay, so the MPI is actually slightly, the OpenMP is slightly faster by about 20%, but the answer is the same. Okay, so what we've seen here is that on an ARCHER2 node, you have the choice of running MPI or OpenMP. I was going to say MPI is faster, it isn't here, but they're roughly the same speed. But OpenMP is much easier. Okay, but the problem is you cannot go beyond a node with OpenMP because it's limited to a single node. So what people often ask is, can I combine MPI and OpenMP? Can I use MPI between nodes and OpenMP on a node? And the answer is yes, you can. And that's what we're going to look at, whether to combine these two programming models. So I thought it was worth going through that, both to familiarize yourself with the exercise and to basically explain to OpenMP, those of you who maybe aren't that familiar with it, how it works. So I just wanted to, having done that, I wondered if there are any questions before I go on to give the actual talk. Thanks, Werner, for the hit. Are there any questions about that? So hopefully the traffic model is something to have in the back of your mind, and it's the one we're going to do the exercise on. It won't really illustrate particularly well the performance issues, but that's because it's such a simple program. Okay, so if there aren't any questions, I will now go to the lecture. Which is somewhere here. Okay, so MPI and OpenMP. So I'll talk about the motivation, the potential advantages, and the potential problems. I'll spend quite a bit of time on the problems because a big mistake that people make is they say, "Oh, I think that my MPI program will go faster if I did the parallelization on a node using OpenMP," and they do that. They spend a lot of time doing that, and they find out their code doesn't go any faster. And so you need to really, there are cases where it might go faster, potentially significantly faster, but you need to think about it before you dive into it. What I'll do is I'll stop at this point here. There's a lot of slides here. We're going to do them over 2 lectures. I'll stop here, and then there'll be a practical session where you can play around with that traffic model just to get familiar with it. And then after the coffee break, I will actually talk about the different styles of MPI and OpenMP programming, because there's different ways you can mix and match the two, which get more complicated and have more constraints, and they have implications on how you use MPI. So the motivation, everywhere has multi-core chips. Almost all current CPU systems are clustered architectures like ARCHER2. It's a bunch of separate machines, separate computers, 6,000 nodes, all of which have 128 CPU cores. Each node consists of a shared memory multiprocessor SMP. So you have a single address space within each node, which means you can share arrays. We saw that in OpenMP, you said that the road is shared between threads, which you can't do in MPI, or you can't do easily in MPI. We'll see later on today how you can do it. But separate nodes have separate address spaces. So how should we program such a machine? We could use MPI across the whole system, i.e. for 2 nodes run 256 MPI processes. We can't in general use OpenMP or threads across the whole system. Some people have, people have developed operating systems versions of Unix which actually run on multiple nodes on multiple computers, but they don't really work very well. So the obvious thing is, can I use OpenMP and threads within a node and MPI between nodes? Now I say OpenMP, MPI talks about combining threads and MPI, but almost universally in high-performance computing, we use OpenMP for threaded programming because it's designed for. There are other threading models. C++ has its own threading model. There's POSIX threads. There's Boost thread. All kinds of stuff. But when I say threads here, I'm really thinking about OpenMP because that's what we use in high-performance computing. So expectations in general, MPI and OpenMP does not improve the performance. It may be worse in the regime where the MPI application is scaling well. However, the benefits come when the MPI scalability runs out. And scalability comes in terms of either time, or we'll talk about memory. And MPI and OpenMP may extend the scalability to larger core counts. So what you expect to see is your pure MPI program will scale like this. If you do hybrid MPI and OpenMP, there are various overheads, but you may be able to extend the scalability out to a higher number of cores. That means it's a difficult software engineering challenge because, of course, you're developing down here. When you develop, you run on small numbers of cores, but you'll only see the benefit at large numbers. So what are the potential advantages for hybrid MPI plus OpenMP? Well, there are really 4 possible scenarios where it would help you. One is reducing memory usage. The other, exploiting additional levels of parallelism. Third is reducing load imbalance. We talked about very briefly yesterday how load balancing in MPI is difficult, but actually OpenMP has built-in mechanisms for load balancing, and potentially reducing the communications cost in certain situations. So what about reducing memory usage? Well, some MPI codes use a replicated data strategy, where all processes have a copy of a major data structure. Now, the thing that you might immediately think of is an example I think I mentioned yesterday in my motivation talk, is a lookup table. You might be doing some combustion code where you have lots of chemical reactions going on. You have a big lookup table of how species molecule A interacts with molecule B, a big lookup table of reaction rates based on concentrations and temperatures and densities and all kinds of things. Could be a very big lookup table. In MPI, every process needs a copy of this major data structure. However, in OpenMP, you wouldn't need that. In OpenMP, you could just declare this data structure as being shared, and all your threads could access the data structure. And so that would reduce your memory by a large factor. You would need 1 copy of this data structure per ARCHER2 node, not 128. However, you might say, well, I don't have any replicated data structures. But classical domain decomposition, you have halos, ghost cells, and we'll see that they are effectively replicated data. You have a copy of the data from another process, and that can become quite significant in certain situations. MPI uses up memory. We said that, for example, MPI reserves space for standard sends. It will have internal buffers for storing data. If you have 120 MPI processes per node, you have 128 of them. If you only have 1 process per node, you only have 1 of them again. So a pure MPI code only needs 1 copy per core, but a hybrid code would only need 1 copy per node. And the data structure can be shared with multiple threads. So when you do intranode messages, if you communicate between the threads on a node, you don't need MPI buffers because you do that with a different mechanism. You do that with the way that OpenMP, what you do with OpenMP is you read and write to a shared array. So this becomes increasingly important because the amount of memory per core is not likely to increase in future. So I mean, modern computers have vast amounts of memory, but not so much memory per core. So for example, on Archer, our previous system, we had 64 gigabytes per node, but only 24 CPU cores, so they had about 2.5 to 3 gigabytes each. On ARCHER2, the amount of memory per node has gone up by a factor of 4. We have 256 CPU, 128 cores per node, but the memory's only gone up by a factor of, the number of cores has gone up by a factor of about 5 or 6. So we have only 2 gigabytes, not 2.5. So the amount, and that's going to get more extreme in the future. So we expect that the amount of memory per core is going to get less, and so these issues of limited memory will become more severe. So as I said, the halo storage can actually become quite significant. As we use more processors, you have a smaller domain size per processor. Again, we typically will do strong scaling, keep the problem size fixed, and increase the number of CPU cores. And the amount of halo data increases and starts to occupy a significant fraction of the total storage. So for a simple example, if you're running, if you have a local domain size of 50 cubed, you have 125,000 data points. But your actual arrays will be one larger in each dimension to store the halo data, which from 3D, your domain is a cube, and your halo data are 2D faces of the cube. And so we have 52 cubed. So 52 minus 50 cubed is 15,000. So we have 11% of data in halos. However, if we start to use more processes, then the local domain size gets smaller. So if we've got a 20 cubed array, we have 22 cubed minus 20 cubed, this much storage in the halos, which is 25%. And if we only have a 10 cubed array, then we get up to almost half the data being in the halos. And so a lot of tricks. Some people have deeper halos. You only have a halo if your update depends on the nearest neighbors, then you need data from your nearest neighbor, which is a halo of depth 1. But if your update depended on your neighbor and your next to the nearest neighbor, in the parallel code, you'd need halos of depth 2, which would mean that you would have here 14 cubed minus 10 cubed. And what's 14 cubed? I can't work it out. 14 cubed is 2,744. So in fact, you would have much more. You would more than double your data storage. This would be 2,500 minus 1,000. So this would be more than 100%. Also, in greater than 3 dimensions. So, for example, some programs operate in more than 3 dimensions. A lot of sort of magnetohydrodynamics codes I've heard about not have 5 dimensions. They have dimensions to do with they have momentum dimensions and other dimensions, and so this can get much worse. The other point where people have had a lot of success with hybrid MPI OpenMP is exploiting additional levels of parallelism. So I should maybe there isn't a diagram here, which is poor. So I should maybe basically give an example. I'll try and draw. I use a whiteboard. Apologize, I do have a diagram for this. So imagine that you are you've got a cubic domain, okay? And you want to parallelize this. The simplest way to parallelize it is to parallelize it into 1D slices. Like this. So if we were on 6 processes, each process would get, I'm not drawing this very well, would get a slice. So we've divided it into slices. And people often do this, often if you're doing parallel Fourier transforms, this is nice because it allows you to do an entire 2D Fourier transform each process. Then you do a transposition and finish it off in the other dimension. So you often see this domain decomposition strategy when you, for codes which do parallel Fourier transforms. The problem with this is that you are limited in this case. If this dimension here was, for example, 512, okay, this parallelization strategy limits you to 512 processes because you cannot parallelize this over more than 512 processes because you can't have less than one slice per process. So this simple parallelization strategy would limit you for a 512 cubed array to 512 MPI processes. However, now, if we just, what we could do is we could say, well, we're going to run one MPI process per node. So this slab is now, we have one slab per node, and we will do the parallelization across a node using OpenMP threads. In that point, in that situation, the scalability would increase to 512 nodes, i.e. 128x more cores. Now, the alternative thing would be to say, well, I'm going to do a better parallelization. I'm going to parallelize in this dimension as well. Okay, so you would do something like this. This is called a pencil decomposition because if you think about it, rather than each process getting a whole slab, each process gets a kind of a tube or a pencil. However, that implies more communication in your code. You have to do more transposes, but also, you may not be able to do that. You may have written your code a lot. This code may be hardwired into the code that the decomposition is a slab decomposition. So what we're saying here is you've taken a design decision early on in designing your MPI code, possibly for simplicity, that limits the scalability. And that the classic example is this 1D versus 2D decomposition. So what you do, rather than doing this, you stick with the 1D decomposition for MPI and exploit additional parallelism within a node by using OpenMP threads. So I should maybe put that diagram into the exercise, into the lecture, sorry. So I go back to the slides. So some MPI codes don't scale beyond a certain core count because they run out of available parallelism at the top level. There may be additional lower levels of parallelism that can be exploited. In principle, this can be done using MPI, but in practice, it may be hard. So the example I gave was it may be hard to work around design decisions in the original MPI version. But for example, imagine you were simulating a bunch of houses. You wanted to simulate maybe the energy consumption of houses. And you might have said, well, I'm going to give a different house to each MPI process. Well, if you've got 512 MPI processes, then you can't simulate more than 512 houses. And you might want to run on more than 512 MPI processes. It might be very difficult to parallelize the calculation within a house. Across houses is easy. You run the same simulation on different processes. Within a house, parallelizing the way that maybe the central heating works or the airflow might be difficult. But with OpenMP, you can say, well, within a house, I'll do the parallelization using OpenMP, but I'll distribute the houses between different MPI processes. So as I said, you may use threads to eat up extra parallelism, either because the lower level parallelism may be hard to load balance or may be difficult to do, or the more common one is it may be hard to work around design decisions in the original MPI version, and that's a classic point. So you may exploit these additional levels of parallelism using OpenMP threads. You can take an incremental approach, loop by loop, but OpenMP parallelism cannot extend beyond a single node, but this may be enough. This is because future systems will have more cores per node rather than many more nodes, actually. I mean, it's interesting that ARCHER2 is, for science, more than an order of magnitude more powerful than ARCHER. In terms of CPU cores, it has about 5 times as many CPU cores, 750,000 versus 128,000, but it has about the same number of nodes. ARCHER had about 5,000 nodes, ARCHER2 has 6,000 nodes. The increased number of CPU cores we're seeing is happening because of many more cores per node, not many more nodes. The number of nodes hasn't increased significantly in 2 decades, 3 decades. Back in the very early 90s, the Cray T3D had 256 nodes. Okay, but each node only had a single CPU core. So even 25 years ago, there were machines with 1,000 nodes, but they only had 1,000 CPU cores. So that's where the increase in scalability is coming. The increase in machine size is coming. The other one is reducing load imbalance. We saw that load balancing between MPI processes can be hard. When you would transfer the work, you also have to transfer the data, and that gives you an overhead. So transferring small tasks may not be beneficial, and so it's very difficult to do a global load balancing. So you may restrict to what people call a diffusion model. You only restrict to transferring loads between neighbors. You say, well, I've got more work than my neighbor, I'll give her 10% of my work. And actually that may not be optimal. You might want to do something more global. Load balancing between threads is much easier. OpenMP has ways of load balancing automatically. When you do a parallel for, you can tell OpenMP to distribute a for loop in a dynamic task farm just with a single, you just say schedule dynamic. So OpenMP has built-in load balancing models which can be dynamic task farms. And the reason that works is you can transfer work between tasks, in this case threads, without transferring the data because they all have access to the same shared memory. Overheads are lower, and so fine-grained load balancing is possible. And it's easier to have a global view. So for application with load balance problems, keeping the number of MPI processes small can be an advantage. Your load balancing strategy in MPI may scale to a few hundred MPI processes, but not many thousands. And so the idea here is you load balance between nodes with MPI, but then at the finer grain, you load balance between CPU cores using threads. And that's a model which might work for you. The other example is reducing communication costs. You might naturally think that communicating data inside a node is faster between OpenMP threads than between MPI processes, because to transfer data between two MPI processes, you have to call a library call, MPI send and MPI receive, and there will potentially be copying into internal buffers. To transfer data in OpenMP, because it's a threaded model, you have a global, I think of it as a shared whiteboard, a shared array, and different threads can just read and write to the same memory location. However, in practice, there are lots of caveats, which I'll come back to. And in fact, this is really the bottleneck in MPI code. Communication is the bottleneck in MPI codes. As we saw with the ping pong example yesterday, communication within a node is, up to an order of magnitude faster in terms of latency and bandwidth than communication between nodes. However, some MPI codes communicate more data than actually required. And this is particularly true when there are irregular or data-dependent communication patterns. If you have a very simple static communications pattern like the traffic model, like a classical domain decomposition halo swapping code, your MPI communications is probably quite efficient. However, there are situations where it's difficult to do communications efficiently in MPI. And there are instances where when MPI implementations weren't particularly efficient or hadn't been optimized for shared memory nodes, it was sometimes beneficial to do collectives yourself. So what you did is you said, MPI isn't particularly efficient, say, for an all reduce because it's using processes. I will do the all reduce within a node using OpenMP and only do the reduction between nodes using MPI. However, nowadays that's rarely the case. So I would think that this is becoming less of an issue. The reason is that when an MPI routine, a collective routine, is inefficient in a hybrid shared memory distributed memory architecture like ARCHER2, the MPI developers go away and spend a lot of time optimizing it, possibly using low-level shared memory tricks. So doing it yourself is not such a big win nowadays. There was an example, though. European Centre for Medium Range Weather Forecasting has a very large and complicated code called IFS, the Integrated Forecast System, and it has something called a semi-Lagrangian navigation. The important point is that in weather, when the weather, a lot of information transfers with the wind. So, for example, if the wind is blowing from west to east, you need to know you have an easterly wind, okay? You need to know a lot of information from your labor to the west, because that's where the weather is coming. You need to know the temperature and the pressure and the cloud structure, but you don't care what's happening on the other side, because that's not the direction the wind is blowing. So the direction you communicate depends dynamically on, for example, the direction of the wind. However, that's very difficult to cope with an MPI. So an MPI, what they do is they communicate all the data that could possibly be needed. They collect all the data from all their neighbors, but then only use the data in the direction of the wind. And I've got a diagram to illustrate that. That's because it's actually very difficult to do data-dependent communications in MPI. However, in MPI plus OpenMP, within a node, you can read the data directly, and so you just read the data if you need it. A significant reduction in communication costs and a significant reduction in memory usage. So the reason is that they have very deep halos, because the wind can blow quite strong. They have I've illustrated with depth 2 halos, but in fact, it's actually often a lot bigger. So if this were a process decomposition of 9 processes, this process here would have to get data from all its 8 neighbors in a deep halo region, but it only uses this data because the wind is blowing in that direction. So actually, the only data it needs is this small amount of data here. If these were threads, you could make this a shared array, and this thread would only read this data and ignore this data. And so it's a significant reduction in the amount of data you have to communicate. And so it has both benefits. It reduces the amount of MPI communication, also reduces the memory usage, because you have these deep halos. You have 1 halo region per node, as opposed to 1 halo region per CPU core, and that's a factor of 128 on a machine like ARCHER2. So, but what are the problems with MPI and OpenMP? And there are 4 major problems: development and maintenance costs, portability, numerical libraries, and performance pitfalls. So I'll cover these, and then we'll break for the coffee, and then we'll break for the practical, where I'd like you to spend some time getting familiar with that exercise, just to understand what it's doing. So, you're combining 2 models, MPI and OpenMP, so you need to understand both of them. It may be hard to have a developer who understands that. And the development maintenance will be harder than for a pure MPI code. I mean, OpenMP programming is easier than MPI in general. You saw the differences between my OpenMP code and my serial code for the traffic model were half a dozen lines or so. The MPI code was very different from the serial code, but it's still parallel programming. And as I said, your application developer needs another skill. The other problem with OpenMP, this is true of all threaded programming, is it's subject to very subtle race conditions and non-deterministic bugs. Because threads can read and write to the same memory location without explicitly communicating, unless you're very careful about your synchronization, you can get subtle race conditions, and correctness testing can be hard. And that can be even harder when you combine it with MPI. Portability, OpenMP and MPI are themselves highly portable, not perfectly, but they are. But combined MPI and OpenMP is less so. We will see that the most advanced or general way of programming in hybrid MPI OpenMP places quite strict requirements on your MPI library. It requires your MPI library is thread safe, that different threads can call the same MPI library at the same time. That may not be true. Your MPI library may not be thread safe depending on the implementation. Also, I mean, it's actually useful with an OpenMP code, because it's based on these directives. You can actually tell the compiler a well-written OpenMP code will compile with a serial compiler, because it will just ignore all these OpenMP directives. That's what you would actually want for debugging, is to have a hybrid MPI OpenMP code that could run both with pure MPI and pure OpenMP. That's going to be quite hard to do technically. So again, maintaining your code so that it's easy to debug is going to be hard. Libraries, you should never reinvent the wheel, and so if you're doing linear algebra, you call the LAPACK library. If we're doing FFTs, you call something like FFTW. However, if the pure MPI uses distributed, say you have a parallel library, okay, so for example, you have a parallel FFT library, In your hybrid MPI OpenMP code, that library may not be able to take advantage of threads. So for example, if we're running on 4 nodes, which on ARCHER2 is 512 CPU cores, we might only be running 4 MPI processes. And within our own code, we're exploiting the 128 CPU cores by using OpenMP. If the parallel library isn't threaded, if it can't use threads itself, it will only run on 4 processes. You're wasting a lot of CPU cores. So you will have to make sure that your library, for example, your parallel FFT library, can use threads. That's also true if your pure MPI code uses a sequential library. If it calls a serial library, again, you will only be calling that on 4 CPU cores on 4 nodes, not 512. And so there are issues there. The other problem is the opposite problem, that if your library uses threading but doesn't use OpenMP, you may have 128 OpenMP threads, but then your library creates 128 of its own threads, and you end up with oversubscription. You're running too many threads per code. So you know, both the application library and your application may create threads. So this is less common now, but it is a problem if the library is parallelized using threads but not using OpenMP. We saw that you specify the number of OpenMP threads using OMP num threads, but your library may have its own model. And the final one is performance pitfalls. Adding OpenMP may introduce additional overheads. I don't have really time to go into these, but there are synchronized overheads. There's a thing called false sharing in OpenMP, non-uniform memory access effects, which are quite. The main issue here is it adds a tunable parameter, the number of threads per MPI process. So I've always said that, you know, we have 4 nodes, 512 CPU cores. We run 1 MPI process per node and 128 threads per node. But we could run 2 MPI processes per node and 64 threads, or 4 and 32, or 8 and 16, or 16 and 8, or 32 and 4, 64 and 2. There's a huge number of combinations of threads times processes, which will use all the CPU cores. And finding it's very hard to guess that, and so you end up doing a lot of experimentation, you know, and that can be hard to do. And I haven't really mentioned much about this, but the placement of processes and OpenMP threads within a node you have to worry quite carefully about where your processes and threads are in a node, and that is a trick. That is tricky. But the one thing which people really often forget is that the advantage of OpenMP is that it's an incremental parallelization strategy. You find your most expensive loops, you parallelize it. You find the next most expensive loop, you parallelize it. The problem with hybrid MPI, imagine we have a machine which has 6 CPU cores per node. When I run a pure MPI code, I'm running a process on each CPU core. I'm using up all the CPU cores. When I do hybrid MPI plus OpenMP, I don't run 6 MPI processes, I run 1 MPI process. So immediately my code will go 6 times slower. However, I gain that back by parallelizing using OpenMP. However, everywhere I don't parallelize using OpenMP, I'm wasting performance. So that's the big problem. When you do hybrid MPI OpenMP, if you immediately start off with a performance hit because you're running fewer MPI processes per CPU core. You then have to parallelize these loops with OpenMP. You even have to parallelize the loops which previously worked perfectly happily in pure MPI. So the problem is you have to put OpenMP into your whole code, all of it, not just those regions which are performance critical. And that is potentially a big software engineering challenge. And that really is just Amdahl's law, but it does mean that, you know, you have to make global changes to your code. And if you're lucky that all your time is spent in a couple of loops, that's fine. But if your time is spread over large subsections of code, over thousands of functions, putting OpenMP into all those functions could be a massive overhead. That's from a software engineering point of view. There are some of the issues here, but there are the details. I'll just skim over them really. I mean, I'll just, yeah, there's just lots and lots of other, unless you're an OpenMP expert, you might not understand these, but there are issues to do with memory location and things. The one I do want to talk about is NUMA effects. It may not be obvious, but in a node on ARCHER2, for example, has two CPU. Often you have multiple CPU cores per node. Many systems have 2 CPUs per node. Every node has its own, every CPU has its own memory. So you might ask, well, when I allocate memory, but the way it's tied together, all the CPU cores can access all the memory, but they're actually, I should maybe, I have a diagram here, but give me a second. Just to illustrate this, apologies, the slide doesn't seem to be, the slide I need doesn't seem to be here. Apologies about that. Okay. So I don't seem to have that. Okay, apologies about that. I don't have the slide that I need. Sorry about that. That's seems to have. Okay, no, okay. So apologies, I don't have this slide that I was hoping for, but it comes from another course, so that's apologies why I'm not able to find it. But the point is that okay. You have these. A node on ARCHER2 is physically 264 core processors with their own memory, but they can all access each memory. But access to their own memory is faster. So you might ask, when Linux does an allocation, where does it put the data? Well, Linux typically has something called a first touch policy. So basically, it allocates the memory on the CPU which first accesses that memory. That's called a first touch policy, and that's the right thing for MPI, but it's worse for it because in OpenMP, it's possible to end up with all the memory allocated on the wrong CPU core, and these are NUMA effects, non-uniform memory access effects, and they can limit the scalability of OpenMP. Basically, it's very difficult to get OpenMP to scale beyond a single CPU. So on ARCHER2, it's hard to get OpenMP to scale beyond 64. Actually, on ARCHER2, it's even less. So it's probably 16 for other reasons. So it's just that there are subtle effects which can affect you there. Process and thread placement. Again, you want the MPI process spread across sockets. The OpenMP threads within the same socket. That can be hard to arrange. And okay, so that was that. I want to skim it up. So what I'm going to do in the next lecture is talk about the 4 styles of hybrid MPI OpenMP. But I've really just covered there a lot of caveats and things just to give you a warning up front that this isn't a magic solution you need to think about. So what I would say is, before embarking on a hybrid MPI OpenMP strategy, you have to have a clear reason for saying, I believe that my program will go faster for these reasons. Then it's probably worth doing. But that's really, I wanted to stop there because that's halfway through the talk, and then there's a natural break. But I think the exercise I wanted you to do, I will now show you the exercise sheet, which is on the hopefully you can see that now. Yep. So down here we have the code, which I've already shown you how to get, but the exercise sheet is really just a warm up where okay, so for this purpose I'll go to the direct GitHub link so it opens in line. So there's really a whole bunch of things here which I want you to do. There are MPI exercises which you can play around with. You can look at solving the send receive with iSend and await all. Persistent communications overlap. There's lots of ideas here. You can play around with the OpenMP exercises on their own, okay? And then the hybrid MPI OpenMP is what we're going to do. But really, for this next half hour, the idea was that you would maybe pick some of these MPI or OpenMP exercises just to familiarize yourself with the code and get a feeling for how they're parallelized. So that was the exercise. So the exercise is to just take that that code, download it, compile and run it, and maybe play around with it and see just understand how the two versions work, the OpenMP and the MPI. And then what we'll do now is we'll learn in the next lecture how to combine them. So I will. How do I clear this? I'm sure there's a better way of doing this. Yeah, I'm not very expert with this interface. So okay, there we go. There we go. I'm sure there's better ways of doing it than this. And must be an easy way of clearing this.
I think there's a button at the top right, David. Clear all annotations.
Okay. Okay. Thank you. Thank you. Sorry about that. I said so what I will do, I'll put a comment up here. So as a practical. So that's what I'm going to do now. I do find this interface slightly confusing. There we go, that looks better. So familiarize with yourself with the pure MPI, pure OpenMP traffic model, practical until 1100, and then there's a coffee break, and we'll have next lecture at 11:30, which are different styles. And I'll be around, I'll be online